Good afternoon, my name's Doug. I'm going to be talking about measuring the latency of databases with both DRAM and persistent memory for both in-memory databases and disk-based databases. So I'm a developer and product manager at Oracle Database Development. At Oracle, we're very interested in database performance, specifically latency and throughput. So this talk is sort of a summary of research that we've been doing for the last few years with respect to persistent memory and whether it can help databases. So we wanted to answer some fundamental questions. Can Intel Optane Persistent Memory improve database latency with respect to buffer cache reads, log writes and commits? And also, can Intel Optane Persistent Memory improve the latency of in-memory databases for reads, writes and commits? If this is so, should you be using app direct mode, memory mode, or both? So what is app direct mode and memory mode? With Intel Optane Persistent Memory, there's basically three ways that you can access memory. If you're using app direct mode, you have the choice of directly accessing DRAM for ultimate performance, or choosing to use the Optane Persistent Memory, which is slightly slower but has the advantage of giving you persistency. So you can use for the DRAM, so that's for the fastest thing, which are transient, and for the data structures that need to be persisted, you can write to the Optane Persistent Memory. So with app direct mode, you have complete control, but it requires you to make explicit design decisions and code changes. A different mode is memory mode. So in this mode, you don't have any control over how memory is accessed. It's just one big blob of memory, and you don't know whether you're accessing DRAM or persistent memory. So the advantage of that is it's simple, it just works. You don't need to change your application. You don't need to recompile. You just have to have a machine with persistent memory which is configured correctly. So app direct mode gives you control, but you need to make changes. With memory mode, it just works out of the box. And the thing that may not be obvious is when you're using persistent mode, the persistent memory is not actually persistent. It's just DRAM. So this talk is looking at those combinations and how they affect databases, the pros and cons, and looking at some results there. So first of all, we'll look at using app direct mode for a disk-based database. So virtually all databases for the last 40 years have been designed the same. You've got spinning Rust where your data is stored or persisted, and you load that data into your memory as needed. So you'll tend to have far more disk space than memory, so you can load chunks or pages of data as required. So whether you've got spinning Rust, SSDs, NVMe disks, or persistent memories, they're all fundamentally doing the same thing. It's just as you go up the hierarchy, it gets faster, so you're getting lower latency and higher throughput, and obviously with increased cost. So what we looked at doing was having an automatic memory hierarchy from the slowest to the fastest to see how that could benefit buffer cache reads. So we used app direct mode, so we had to explicitly design this automatic memory hierarchy. So the great thing is, the result was we were able to get up to 10 times faster reads using this hierarchy. So the hottest data we were getting from persistent memory, the warm data we were getting off NVMe disk, and the coldest data we were getting off SSDs. We weren't using spinning Rust because it's just too slow for what we need. So this approach was giving us up to 10 times faster reads. So with doing ACID transactions and consistent reads, we're able to do that in up to about 19 microseconds. Sometimes more, sometimes less, but on average about 19 microseconds. So for buffer cache reads, using Intel Optane Persistent Memory and apt-direct mode was very effective. When we're doing writes, whether we're writing redo and undo for our transaction logs or doing commits, once again using persistent memory and apt-direct mode was significantly faster. In our case, up to 8 times faster than the fastest NVMe disks that we could have. So it's pretty good, consider it magical. If you contrast that to using persistent memory for memory databases, it's not so simple. The fundamental difference for in-memory databases is all of the data needs to be in memory all of the time. As such, you need to have a large amount of memory. So Intel Persistent Memory, Optane Persistent Memory is good, but it is finite in capacity. The max module size is currently 512 gigabytes. Another thing to consider is Optane Persistent Memory only works with Intel CPUs, and specifically the latest generation CPUs. Also, persistent memory is actually slower than DDR4 RAM. So you need to make very hard design choices whether it's worth it for in-memory databases. So if you're going to use apt-direct mode for an in-memory database, there are pros and cons. Some of the advantages of using persistent memory with an in-memory database is if you have already created your database and you use persistent memory, you can reload or recover that database basically instantly, certainly under a second, even for multi-terabyte databases. So if you contrast that to another storage device, you need to measure that in gigabytes per second on how fast you can load that database. But with persistent memory, you just need to attach to that file system basically, and you've reloaded your database. Another advantage is if you're doing synchronous writes for logs or commits, you can do that very fast and it's simple, it just works. So those are the advantages. The disadvantages if you're using an in-memory database is persistent memory can be up to 3 times slower than using DDR4 RAM. So that's affecting both your latency and your throughput. So if you don't change your code and use apt-direct mode and just point everything to the persistent memory, it will work, but your in-memory database could end up going up to 3 times slower. So that's normally not a good thing. So you need to make some fundamental design choices. You could come up with caching techniques to do that, but that ends up being a big redesign. So let's look at some alternatives. Memory mode for Optane just works out of the box. You don't need to change your code, you don't need to recompile. So what does that mean? With any application, in this case we're using an in-memory database, depending on your workload, you're going to tend to have data that's accessed more, or the hot data, and data that's accessed less frequently, or the cold data. Ideally, the hot data would go in the fastest memory, in this case DDR4 memory, and the colder data could go in the slower memory, in this case Optane Persistent Memory. One of the nice things that Intel did is they made that data placement automatic, so that's a function of the Xeon CPUs. So they claim that that just works. So what I've done is I did a series of tests to measure just how well that actually works with respect to latency, throughput, and different workloads and working sets. So when you're using apt-direct mode, you explicitly use DRAM or persistent memory. But when you're using memory mode, you have no control over what type of memory is being used. So you need to look under the covers. You cannot just have a machine with persistent memory. For each memory module of persistent memory, you need to have a buddy, which is DRAM, which allows caching of the persistent memory in DRAM. So you're always going to have a ratio of DRAM to persistent memory. On the machine I was using, I had 384 gigabytes of DRAM and 1.5 terabytes of persistent memory. So that gave me a 1-to-4 ratio of DRAM to persistent memory. So depending on how much money you want to spend, you might have less DRAM as a ratio to persistent memory. It might be 1-to-8 or 1-to-16. So those are physical hardware choices you make, but they have implications with respect to performance. So when you're in memory mode, you're always accessing DRAM, and you might be accessing persistent memory depending on how much data you're using. If your workload or the working set all fits within DRAM, in theory it should be as fast as DRAM. If your working set takes up all of the memory in the computer, obviously you're going to be using a proportion of DRAM and a proportion of persistent memory. So it really comes down to the cache hit ratio of DRAM versus persistent memory. So what does that really look like in practice? So I did a series of tests to vary the working set size to see how it affects performance. Now, one of the things is, because this is all happening automatically, you don't really know what's happening because Intel's made that transparent. So you really need to look under the cover using hardware events to verify what you think is happening is actually what is happening. So this is just looking at the working set size. So instead of using a working set size that takes up all memory, you might choose to have a subset. So whether it's a very simple function or a more complicated function, there's different ways of doing it. So I had many discussions with people about what is the ideal distribution. I ended up doing all of them. The interesting thing was the results didn't really matter. So here's just an example of looking at the hardware events using Grafana. So you can either write a C program to look at those hardware events, or you can let Prometheus and Grafana do all the hard work for you. So I used Grafana because it did what I needed. The point being, you can do a test and you can look under the cover and see cause and effect of what you think's happening versus what's actually happening. So here's a result. What we're looking here is actually 3 distributions. There's a distribution here for DRAM, there's a distribution for persistent memory, and you can just see there's a distribution there for L3 caches. So based on the scale, you can't see it, but there's actually some values there and some values there. So it's kind of a normal distribution. So what we're seeing here is, based on the working set size, we're either hitting DRAM, which for my workload is taking about a microsecond, or if I change the working set size such that it will not fit in DRAM and it's hitting persistent memory, it's taking about 2 microseconds. If you get really lucky, you might hit L3 cache. So what we're saying here is the persistent memory is about twice as slow for this hardware, for the workload I was using, is DDR4 RAM. So it's about twice as slow. So that's not so good. Or you could say, hey, it's still pretty fast because it's 2.1 microseconds. So is the glass half full or half empty? The point being, it's very noticeable distributions. The other aspect is, there's actually 2 sets of tests here. When I have a range or working set size which is very small, in this case for the blue, only covering about 10,000 rows, or a large working set which with about 100 million rows, which is taking up almost the entire working set. So the interesting thing is, the performance of those 2 very different working sets, one which is guaranteed to fit in DRAM, is almost exactly the same as the latency and throughput for where the working set has to use mostly persistent memory. So that's a very good result. So let's drill down into that a bit more. When I force the workload to always fit within DRAM, the memory mode results and the DRAM results for reads were exactly the same. So that's a very good result. So that means the memory management built in the Intel CPU, this so-called magic thing here, worked very well. Likewise, for the writes, it was almost as fast. It was about 5% slower. So that's just an artifact of how persistent memory works. So it's pretty fast, but not quite as fast. So that's one set of results. The second set of results was when I was forcing the working set to be absolutely huge, taking up almost all of the memory. So that means I'm using some DRAM, but mostly persistent memory. So my expectation was the cache hit ratio would significantly affect the performance. But surprisingly, it didn't seem to have that great an effect. So that's a good outcome. I like a win. So in this case where we're mostly using persistent memory, even though the latency you could see was basically twice, 2 milliseconds versus 1, the scalability wasn't really as affected as if I was using all DRAM. So I obviously had multiple machines exactly the same, some configured with just DRAM, some with a mixture of persistent memory. So I did many tests for many weeks. So the point being, read latency was definitely measurable, but the scalability or the throughput wasn't really affected by the persistent memory. The write scalability was more noticeable, and you could see it, but it wasn't that bad. So I have a huge amount of results, but given the time frame, I can't really go into that depth. So I don't work for Intel, but this technology works quite well. So what was the actual workload that I was running? So I work for Oracle. I do database stuff with SQL. So I had a table. So it's pretty simple table, pretty simple data types. So I inserted 1.4 terabytes of data, and for the width of these tables, that used up about 160 million rows. So that was the structure of the table, and I was populating 1.4 terabytes of data on a machine with 1.5 terabytes. So I was almost using all the memory. I tried it with 1.5 terabytes initially, but the system was swapping because the operating system kernel and your program need to have their own memory. So I cut it back to 1.4 and it worked fine. What was the workload? I was doing both very simple reads and writes. So the reads were just a primary key lookup, and the updates were updating a column based on the primary key. So doing these SQL selects were taking about 1 microsecond in DRAM, and we're taking about 2.1 microseconds using Intel Persistent Memory. Doing the update takes a little bit longer. Because we do ACID transaction, you need to deal with undo and redo. So that was taking about 4 microseconds in DRAM and about 8 microseconds in persistent memory. So it was fairly fast, but DRAM is definitely slightly slower. So I used a bunch of technologies to do this. The most fundamental tool is probably the simplest, just get time of day. So I sprinkled lots of get time of day around critical parts of the database kernel. So I could measure down to the nanosecond exactly how long these different read and write events were taking. Your application can use whatever your favorite compiler is, but when you are trying to figure out what's happening exactly down to the microsecond, for Intel CPUs, the Intel compiler and vTune are the way to go. It gives you a lot of insight that GCC will not. To configure the machine to vary the amount of DRAM versus persistent memory, because you can be running in just memory mode or just app direct mode or a mixture. I was using the open source IPM CTL tool, and I was using the process counter monitor to figure out what was happening under the covers with Prometheus and Grafana. For the database, where we're measuring the performance of the buffer cache, I was using Oracle Exadata X8M with app direct mode, and for the in-memory database I was using Oracle x10. So the workload I showed you, it's pretty simple. It was just an ODBC program written in C. You can download it here from the web if you want to try it yourself. So in summary, app direct mode can be very good for disk-based databases which use buffer cache management. For in-memory databases, it's probably simpler just to use memory mode because you don't have to do anything and it works pretty well. So that's what I wanted to say. Thank you.